Hello everyone. Today we're going to talk about a very interesting and exciting project that has the potential to shape up the transportation industry, which is nothing but a fifth mode of transport, that is Hyperloop. Hyperloop was introduced in the year 2013 by Elon Musk, the CEO of Tesla and SpaceX, Tesla Motors and SpaceX, and he wrote a white paper on how a Hyperloop would work and how would it be sustainable, self-sufficient, and also how would it better the existing four modes of transport. So his paper was mostly written in terms of the first a tube or the first track being laid between Los Angeles and San Francisco. What we will try to do today is to actually understand his motivations and how the concept would work. So without wasting any time, let's go directly into the presentation. Okay, so what are the four modes of transport that we know already? Those are air, water, road, and rail. And now let's look into the fifth mode of transport, that is the Hyperloop. This is one of the earliest schematics of Hyperloop designed by Elon Musk. So what is a Hyperloop? Let's answer the basic fundamental question. Now, this idea is not, I would say it's not a very, very new idea in the sense that right from the 18th centuries, humans have been using pneumatic tubes, or there were proposed ideas about vacuum tubes and all. But this is very new in the sense that it doesn't use those ideas, it builds on those ideas. So let's look at how this works. Now, this mode of transport is a proposed mode of transport for both passenger and freight transportation, which instead of using a vacuum tube, it's actually near vacuum, that is low pressure containers or low pressure tubes, which propel the passenger pods or the freight transportation pods at almost the airline speeds, that is theoretically close to 500 miles per hour. Now let's look at so to summarize it, let's summarize Hyperloop first. It's basically just a capsule full of people in a low pressure tube, as written here, which goes really, really fast. That in a nutshell. To understand this completely, we have to go back in time a bit and look at the history of how these capsules were developed theoretically, or how these ideas were developed theoretically. Okay, so let's go back in history. So let's look at mid 1850s first. So this was one of the very first times when a pneumatic railway system was built in several countries in places like Dublin, London, and Paris. And they were meant to transport parcels first, but since back in the day the technology was not really efficient, so the size of the containers were actually large enough to carry people too. Now let's go back in time. So let's move on to 19th century. There were several versions of the pneumatic tubes from mid 1850s to 19th century, but let's look at one of the major commercial uses for which they were built for. So by the end of 19th century, once people were able to master building pneumatic tubes, they built large-scale pneumatic tubes for commercial applications, that is for transporting mail and other messages. Now, I've used the word pneumatic tube a lot of times by now, so let me just step back and explain what a pneumatic tube is. So pneumatic tube would be a container which is very, very closer to vacuum, which uses compressed air for moving solid packages from place to place. So it differs from a regular tube in the sense that usually when we say something called a tube, it is used to transport liquids. The pneumatic tubes instead were used to transport solid packages like a mail and etc. And this is 19th century, and one of the very first models of using a tunnel or a tube for large-scale transportation was theoretically proposed by a NASA pioneer called Robert Goddard. So his idea was to create vacuum tubes. So he theoretically wrote a paper on this idea in 1910 and estimated that if we are able to build a vacuum tube from Boston to New York, So if we are able to build such a tunnel from New York to Boston, so we would have been able to transport people in about 12 minutes, according to his theory. Now moving on to early 2000s, so the next major application or a proposal was proposed by ET3, a commercial company, so which designed a small-scale pneumatic and a maglev train, which is also built on similar principles, which we discussed earlier on pneumatic tubes. So as you can see in the picture, the design features car-sized pods that would travel in elevated tubes. So it would not be on the ground; it would be at a much higher level and elevated level than the ground. Okay, now moving on to the present. By that I mean let's early 2013, 2012, 2013, when Elon Musk wrote his first white paper on Hyperloops. So essentially, now we understood the history of how humans have been able to evolve this technology, that is, be it using compressed air for transporting mails, and then trying to prove that we could use vacuum tubes would be a better alternative for transporting people from place to place. So Elon Musk suggested this idea that so he was actually inspired by all these ideas, and so using low pressure tubes to attain a very airline speeds, that is high airline speeds, so theoretically close to 500 miles per hour. That is because since we are using low pressure containers, there would be very little aerodynamic drag, which will allow us to attain such high speeds. So to uh, to use an analogy in terms of the road transport, a very less aerodynamic drag would be like very less amount of friction. So essentially, we would be going from Flintstones to Jetsons because we'll be attaining such high. We have been evolving in terms of transportation industry. We'll be moving on from this to this. Okay, now let's look at the motivation behind developing this project. So in about 2012, 2013, the Californian government accepted a proposal for high-speed rail system between Los Angeles to San Francisco with about 68.4 billion budget. Now, after this was accepted, Elon Musk argued that with a travel time of about 2 hours 38 minutes by high-speed rail, although it appears faster than the road transport, which is about 5 hours 30 minutes, the cost was still comparable to that of traveling by air. That is like you're paying around $105 as compared to 150 by plane. So he argued that with about similar or a much lesser cost, we could develop a much more high-speed transportation system using low-pressure air containers, which reduces the aerodynamic drag, and also which won't be a hindrance to the existing highway system because you could build this Hyperloop on a much elevated level. So he established the following objectives for Hyperloop. These couple of points, that is the lower cost, it has to be faster, it should be safer, more convenient, immune to weather, especially earthquakes, and lesser carbon footprint, and no disruptions along the route. That is explained by the fact that you won't disrupt. So to build a rail, you have to you're going to disrupt the ecosystem, and you're going to disturb the land in which you'll rail the railroad. You'll develop the railway system. Whereas for Hyperloop, you're just going to use pylon tubes and build these pylon levels, and you build these tubes on top of them, and they're at a much higher elevated level, so it doesn't disrupt anything. And also sustainability. So Elon Musk also suggested that in his first proposal, it is suggested that since there are solar panels built on top of these tubes, the whole Hyperloop can be self-sustainable. So this is one of the schematics between San Francisco to Los Angeles, the first one's developed. And let's look at, so one more argument of his was that if you look at the energy consumed per passenger, so this graph explains it for the existing modes of transport, that is car, aeroplane, the Tesla Model S, Hyperloop, train, and motorcycle. Of course, Hyperloop is still theoretical and it's a proposed mode of transport. So if you look at it, the least amount of energy is occupied by the Hyperloop. So this also proves that this is a much better mode of transportation to use in terms of the energy consumed and also lesser carbon footprint. And this is the top level schematic of the Hyperloop. That is, if you look at the design parameters, so we need the pod, the tube, the mission, and the ticket cost. So, okay, now let's look at the working principle of Hyperloop. So the idea and the basic working principle. So we can break down the Hyperloop system into 7 major components, as you can see here. The tube, the vehicle or the pod, the propulsion system, the suspension system, energy management, timing, and the route. Now, so to sum it up, so I'm going to explain these things in detail later. So to sum it up, these pods are transported. So the tube is mounted on the pylon levels, and the tube is built on the pylon levels, which also has solar panels on top of it. So these capsules are transported in this low pressure tube at a very high speeds, and also to reduce the speed, also at a lower speed. Now, these capsules are also supported by a cushion of air and pressurized air, basically, which also has very less aerodynamic drag. So, how does it accelerate? So, a magnetic linear accelerator is fixed at various stations, and these pods, or the passenger pods, have rotors inside them which assist in this mechanism. So let's look at these individual components, a top-down engineering analysis of Hyperloop. First, the capsule. So the first proposed idea, or the first design level idea of the capsule was it could carry about 28 passengers and along the interior of the tube, and a Hyperloop pod would depart every 2 minutes from Los Angeles to San Francisco. So each capsule or the pod would be separated by about 23 miles on an average during the operation. And as mentioned here, the capsules are supported via air bearings. Next, second most important thing, that's the tube. So this tube is made of steel, these tubes, and each tube, so in the first track between LA and SF, there are two tubes which run side by side and parallel to each other. And the pylons are placed every 100 feet, as shown in the picture here, to support the tube. And the whole system can be self-sustainable because of the solar panels attached on the tubes, so using the solar energy. Propulsion system. I already explained how the acceleration works, that using the rotors inside the pod and the linear accelerators at each station along the length of the tube, which assist in the acceleration of the capsule. And next, the route. So for a Hyperloop to be successful, and since we are traveling at the speeds of around 500 miles per hour, the route has to be as long as possible. There should not be any wide turns. It should be as straight as possible. So if you see the picture, the first route that was proposed, or that was to be laid between Los Angeles to San Francisco, the most of the sections in this are pretty straight. Okay. All right. Now we learned about Elon Musk's vision and the SpaceX the initial designs on Hyperloop. So I would also like to speak about two more companies, that is Hyperloop Transport Technologies and Hyperloop One, which also picked up this idea and after the first white paper and started developing initial versions of the Hyperloop. And last year, Hyperloop One was able to successfully test the first version of Hyperloop in about a 500 meter track, and they were able to attain speeds of about 250 miles per hour, which is not still the quickest or as proposed in the paper yet, but it is actually a really good start, and it is sustainable till 500 meters. So it can be built further. Now, Hyperloop One announced their vision for North America in their conference last year. And so they talk about, since they're able to successfully complete the phase one, they're talking about the plans of the next phase, that is building by 2030, building these Hyperloop tracks all over North America. And this is a really exciting phase ahead, because if you look at it from Boston to Somerset, the trip it's going to only cost 5.3 minutes. And similarly, you can look at Denver to Dallas, 73 minutes. And Chicago to Columbus, it's about 29 minutes. And Fort Collins to Denver in about 7 minutes. Dallas to Austin in about 20 minutes. Los Angeles to San Diego in 12.5 minutes. Seattle to Portland in 17.2 minutes. So if Hyperloop One or Hyperloop Transport Technologies or SpaceX for that matter, any one of these companies is able to pull it off, and if they're able to make this fifth mode of transport a commercially viable application for the passengers, if it suits the demographics, if it works with economies to scale, it is a really exciting time ahead. So I end my presentation here to conclude. So what we did today was basically understanding the basic principles of Hyperloop and how was it throughout the history of humanity, how have we been able to evolve the ideas of transportation. And so this time is really exciting because we are able to achieve about 250 to 300 miles per hour in testing right now for about 500 meters track length. And SpaceX is actively launching competitions, the Hyperloop contest every year annually, in which a lot of students from these prestigious universities take part. So it's really exciting times ahead if you're able to build one of the at least a commercial viable application for humans. Thank you. Till now, we have discussed about what Hyperloop is and historically how it was designed, keeping in mind the earlier designs of pneumonic tubes and Robert Goddard's first implementation of vacuum tubes and all. So now let's move forward and for let's discuss about actually how it works and challenges, engineering challenges it is facing right now. Because theoretically, yes, the idea has been developed and it has been reiterated and iterated multiple times till now. And we have a lot of white papers from Elon Musk, then Hyperloop Transport Technologies, and also Hyperloop One. But practically, where does it stand right now, and what is the future? Let's discuss about that. Right. Now let's discuss about the principles, and then let's see what challenges the model is facing, as discussed with respect to these principles, and also at what is the current development stage of Hyperloop. Now, when we discussed initially about the why, how does it compare with the existing mode of transport, we discussed that one of the main USPs of Hyperloop is the lower cost and the quicker mode of transport and a more convenient approach, and the lesser carbon footprint we discussed because what we're just using air jets to levitate it inside the tube, and then we have across the whole length of the tube there are solar panels attached, so it's also a much more efficient. It contains lesser carbon footprint, and it is much more efficient as compared to other modes of transport which have a much higher carbon footprints. And next, resistant to earthquakes because the pylons, that is the stands along the length of the tube, they are spaced apart and they can withstand the tremors and uh, the whenever there is earthquake of a lower Richter scale, they can withstand that pressure and that tremors onto the tube. And the next is sustainability, which we discussed. It's again with respect to the uh, how to energize the tube. That is the generating the power based on the solar energy, which is a renewable source of energy. Okay, now how does it work? Let's answer the basic question. We can say Hyperloop is a cross between a Concorde, a railgun, and an air hockey table. The reason I say that is Concorde was when it was launched or invented at that time, it was one of the fast and revolutionary mode of transport. A railgun uses electromagnetic forces to transport objects, and an air hockey table is known for the reduction of air friction. If you've played on an air hockey table, you must know how we can easily slide across the table. Now, that's because it has almost next to nothing uh, sliding friction. Now, so according to this diagram, so you can see, so this summarizes how it looks, the tube looks, and what's inside it. Now, as you can see at the both ends, there is the air is at very high pressure. It's almost you can say it's more than the pressure experienced by a Concorde jet. Then inside we have a capsule, and the way capsule is, so we create a pressure difference by which the capsule moves from one place to another place. Yeah. The next important detail is now we talked about the tubes being next, not exactly vacuum, but it does also contain very little amount of air or highly compressed air. Now, this also acts as a cushion to prevent two capsules from colliding within the tube. Now, I mentioned this because we know that since the journey time is less, and also there's about a 10-minute gap, we have vessels running at 10-minute intervals. It's very important to prevent collisions, and now the compressed air in between the capsules acts as that cushion. Now, the next important point is about we discussed earlier that the pretty much the whole length across the length of the track has to be fairly straight. There should be no curves and all. That's because if you look at the second point, the tightest curve radius, keeping the acceleration at 1 g, is about 9 kilometers. That is, if you want to have a curve, the radius has to be 9 kilometers. So the radius is huge. You can't really have uh, track bending or immediate curves because of the speeds of the vessels. Before we go on to discuss the challenges and the practical limitations and the geographical limitations and the engineering challenges faced uh, at the present time with respect to Hyperloop, I would also like to go. This is also one of the iterations. It's called one of the iterations of Hyperloop called the launch loop. The You can see that there are some differences in this. That basically the height of the tube is about 80 kilometers high, which is a lot more than Hyperloop. And also, the instead of steel pylons erected to support the structure, we have stabilization cables, and these are similar to if you've seen suspension bridges. If you look at suspension bridges, the suspension cables, these are similar to these stabilization cables. Okay, let's go to challenges now. So as I said earlier, theoretically this model works, and it's going to revolutionize the transportation industry as a fifth mode of transport. But let's look at the current state of the Hyperloop experiments being performed by both Tesla, SpaceX, and Hyperloop Transportation Technologies and Hyperloop One, one of the leading companies in development of Hyperloop. So the current state of Hyperloop One is that they have built a 250-meter tube in Nevada, and the length of the tube and the size of the track is about 250 meters. And they've been able to achieve speeds up to 240 miles per hour. And I would like to, and this is a part of the new goal called Vision 2030. And I would like to show you. This is a part of Virgin Hyperloop One's Vision 2030 in Nevada. As you can see, their experiments have been successful, and they've been able to successfully accelerate and decelerate the pod within the length of the tube. Now, this is a video released as a part of their phase one of Vision 2030. Right. So since the size of the track, even though the experiment is successful and the phase one is successful, still there we have been the current implementation of Hyperloop is small scale. There are still no large tracks available. So that's the major question. Constructing a perfect tube of hundreds of kilometers of length capable of sustaining near perfect vacuum, is it possible? Now, the first challenge comes in the category of atmospheric pressure. That is, if you look at the leftmost corner of this graph, Boeing 747, when it flies at a height of around 10 to 11 kilometers, and it has 200, so the pressure, atmospheric pressure. And if you look at the rightmost corner, almost 5 times pressure, that amount of pressure is experienced by Hyperloop. So that pressure is at a height of 50 kilometers. But we're building Hyperloop on Earth, so it has to sustain, the whole structure has to withstand this almost 5 times the amount of pressure faced by Boeing 747. So the vessel and the whole structure would be continuously experiencing tens and thousands of kilograms of atmospheric pressure, which threatens to crush any vacuum chamber or any near perfect vacuum chamber. So another issue that the structure would face, which I will elaborate on later, is also thermal expansion. Now, this is because the temperatures change throughout the year, and also the different parts of the track experience different amount of are exposed to different amount of sunlight and different experience different amount of temperatures. So you would have expansion or the tube expanding or tube reducing in size or the bending of the tube. Okay. Now, elaborating on my first point, that is, I would like to show a video on what happens when any body experience such amount of pressure. And this is an experiment performed on a railroad tank car. So as you can see, this it completely gets crushed because that lack of pressure. So as you can see, the whole tube gets punctured, and as soon as there is a difference in pressure, the external layer would tear into the tube and completely would shred the tube apart. So what would be the next major issue? That is now this we have vessels traveling and coming to the stations at almost at the frequency of 10 to 20 minutes. So we would have a constant motion of the vessels in the tubes. So if at all there is a collision, and since the speeds are more than I mean, theoretically, the speeds have been proposed to be around 600 miles per hour. But even if practically we have seen that the speeds are around 300 miles per hour, even at that amount of speeds, the collisions would be completely fatal and also would result in spontaneous compression. Now, I would like to show this example performed by students of Purdue technology students, in which they accelerate and show how a ping pong, just a small ping pong ball, which is completely non-lethal, can become lethal because of the decompression of air and when it attains supersonic speeds. Yes, so they take an example of supersonic wind tunnel. As you can see, they're drawing the air out, and then they're creating the almost the whole vessel. The pipe that you see here is almost vacuum, as you can see. As you can see, as I described earlier, even in the previous example that we saw, we have almost no pressure on one side and very high pressure on the other side. So as soon as you expose any object to a difference of pressure, the air would immediately accelerating the ball. So the ball would attain speeds supersonic. As you can see, it can be completely lethal. The next challenge for the engineers is thermal expansion, which as I said earlier, I would elaborate on this. The change of heat or the change of temperature would cause the Hyperloop tube to physically change its size. Now, as you can see, there are a lot of structures that face this issue, and this diagram is an example of a bridge. As you can see, there is a gap left on either side of the steel platform so that it can expand, and there would be no disturbance in the structure of the bridge even during its expansion. Similar sort of solutions can be applied to Hyperloop View. The next major issue is uneven bending. Now, expansion can be fairly compensated for, or can be fairly kept in check with a lot of taking care of and building support structures and things like that, and leaving amount, some amount of gap within the structures. But uneven bending is one of the major issues which is very difficult to counter. That's because so this so we even if we take an example of the whole of North America, the temperatures vary between 0 to 40 degrees Celsius. So given a temperature variance of 40 degrees, the thermal expansion would result in almost a variance of 300 meters. So that is like we're talking about a expansion or a decrease in length of about 300 meters. Now, along with that, the top of the pipe would be exposed to top of the pipe or the tube would be exposed to more sunlight, so more heat there, and and the bottom portion would experience lesser heat. So even assuming just a minimum of 3 degrees on the pipe, that would cause the top portion to expand 25 meters more than the bottom portion, which causes bending in the tracks. So as you can see, there are a lot of technical challenges and engineering challenges for it to succeed. But with thorough research and uh, due care, this can be all these challenges can be accomplished. Now, before I conclude my presentation on Hyperloop, I would just like to skim through a few numbers just to give us a good idea of how what kind of impact Hyperloop is going to create in transportation industry. Now, these are the diagrams from the Virgin Hyperloop's website. So, where they ask you to specify a source and destination, and they give you these specific numbers based on as a part of their Vision 2030. So, if I selected Los Angeles as my origin and Las Vegas as my destination, so you can see the travel time is completely cut down from. I mean, you go by car, it's around 4 hours 17 minutes. And by plane, it's 3 hours 28. And by a train, it's 2 hours 42. And so with Hyperloop, it's just 30 minutes. So it's almost you're slashing it by 1/6 the travel times. Yeah. So this is the same graph. So from Los Angeles to Las Vegas, you can see, we if traveled at the speed of 1080 kilometers per hour, you can cover the journey in 30 minutes. So what this is the demographics on the population and the total number of passengers per year. That is, you can add in these numbers. Oh, this is also one of the most important ones, that if per million Virgin Hyperloop passengers or passengers accessing Hyperloop, what is the amount of travel time that is saved? 187 is, which is a huge amount. So when you compare it with other modes of transport, so definitely going forward, if we are able to sustain or uh, are able to achieve whatever that was proposed theoretically in the next 10-15 years, and this is definitely going to be the mode of transport that is going to revolutionize the transportation industry. So with this, I conclude my presentation on Hyperloop. Thank you, and